I'm going to present the use case related with application on the quantum safe approach, including the technology that is called quantum key distribution, integrated with the post-quantum and making some analysis on this use case and how they can be used in the 5G network environment. As expected, as an operator, this is really very relevant for us. So, what is the idea? 5G is a really wide or complicated technology and an ecosystem, and there are a lot of places where quantum transition could be impacted on different protocols and solutions. So our focus in the PQ-REACT project was to identify one of the most critical places where the transition and this concept of store now and decrypt later, or harvest now and decrypt later could impact. That is precisely the communication between where we have the antennas and the core of the network. Why? Because this usually goes over open places. The antennas could be in the top of the mall center, could be in the middle of the country, you don't know. So this can impact seriously on the security. What's more, what we wanted to do is to evaluate how the QKD technologies, that is for us considered as a complementary solution, could be integrated with the post-quantum cryptography and the transition towards a quantum safe solution. And for us, this use case, apart from focusing on this part, that by the way we call it the backhaul, or this is called usually in the 5G network terminology, we wanted to compare how they behave when we are using purely post-quantum cryptography and when we are using combination hybridization with QKD. And the reference protocol for this solution usually is the IPsec protocol. This is something we have not invented. This is something that is standardized in the 3GPP, and is one of the risks that we identified during the development of the use case on the project on the PQ-REACT. Indeed, as it has been mentioned in other pilot use case, we bring these concerns on the standardization. In this case, we reflected on the GSMA, that is the association that brings the standard for 3GPP to align with the operator. So we try to bring these concerns. So here you have a high-level vision with the main component that you will expect in a 5G network. In the right side, you will have basically the core of the network with different network functions and the component that provide the authentication, control access, and so on to the network, to the user. In the left side, in the green, you will have all the aspects related with the radio part, the UE, that are the terminal, the mobile phones, equipments. G Node B are usually the part related with the antennas, where we radiate. So between both is what we call backhaul, and here's an abstract vision, because usually behind this you have a lot of access, aggregation, and connectivity where it's placed in the data center, or in the telco premises, the core of the network. So over these interfaces, basically, as I mentioned before, you integrate the IPsec protocol. Nowadays, we have basically a couple of solutions. Recently, during the development of the PQ-REACT project, was approved on the standard on the ITF, the latest version of the RFC to integrate post-quantum cryptography natively on the IPsec, integrating basically the MLChem protocol. But we also wanted to leverage other ITF standards that allow you to basically remove the use of one of the pieces on the IPsec protocol, that is the iKey. That is for negotiating the keys used on IPsec, and are clearly vulnerable against the quantum computers. So our goal is to execute some set of experiments to evaluate and compare the behavior when we are using purely PQC and hybridization with QKD. And part of the goal of this use case pilot is not only executing the experiment, but create a framework for monitoring and controlling the experiment. And for that, we leverage a technology or an open source project that initially was led by AT&T on US, but later on was moved to the ATIS Association in USA for operators that are interested on this kind of metrics and performance evaluation. So, to implement this, basically we use a set of pieces on the use case that include from the infrastructure, that for that we selected the environment that, or laboratory that we call the Nextonics. Nowadays, in the past was called Phytonic. This is the reason we still have 5 in the name. But it's a experimentation environment where we have the telco grade hardware and servers, where we can run this kind of experiment without compromising the production environments. We also use some of the high-performance networking tools like L2SM, we'll show later, that allow us to avoid bottlenecks on the performance, on the calculation, due to the limitation that the virtualization environment usually have with these technologies. And for the part of the 5G, what we decided is to use one of the open source projects like the Open5GS and making the emulation, because the goal of this use case was not to provide user connectivity to the 5G, neither to demonstrate that they can run over the quantum safe solution, because basically it's not the scope of this pilot, but to evaluate the performance. So with this emulation environment was enough for us to make the test. And as I mentioned before, mixing different type of approach on migrating the IPsec protocol towards a quantum safe solution. So in the part of the Nextonics, as mentioned, we use this concept of the L2SM that was developed by one of the partners, PQ Riyadh, that allow you to have a transparent connectivity between different clusters. So we can have clusters running different functionalities, we'll show in a demo in a minute, that have all the capacity for the user terminal, the antennas, and so on, and can connect smoothly and transparently to the cloud cluster where it's running the core, and some of the metrics performance tool we have. Also, as we have mentioned, we wanted to integrate quantum key distribution technology. So QKD is a complicated technology. You require a specialized hardware, a specialized fiber, or a specialized satellite. You need very complicated environments. And in order to try to abstract for this part, because it was not the main objective on the project, we integrated what is called QDito. This is a tool that is developed as an open source project by the UC3N University that emulate a complete and distributed quantum communication infrastructure network. So you can add as many as QKD systems you want. So this allows us, for example, if we want to integrate a complex network with a lot of antennas, we can put a QKD system on each of the antennas over using this emulated environment. So going to the part of how we can integrate the QKD with the environment of IPsec and the protocol, here what we adopt is another tools that Telefonica has been working, in this case with the collaboration of the University, UPN, Universidad Politécnica de Madrid, that allow us to integrate on this RFC 9061, that is a standard for controlling IPsec without iKey, adding the capacity to integrate or incorporate QKD keys. This could be extended not only to QKD technology, it can be integrated with any other technology that allow you to provide pre-shared keys dynamically. QKD is the most secure approach, but there are other technologies in the market that can be used. So our idea is to combine basically triggered by a controller that is expected, for example, on 5G, that the network operator have a control plane where he decides when activate and in which moment need to be used IPsec, user plane, control plane for all the clients, or when the key should be renewed, when should be renewed. So this offers a fine-grained control of the activity, the security and crypto agility, that is a relevant point, on the IPsec protocol. And this control is able to interact with this agent that interact with the QKD system using another standard. As you can see, we try to use as much as possible existing standards that help us to have some kind of guarantee that in the future, in production environment, we can use these pieces together. But basically, take the keys from a QKD network, in this case for the QDITO emulation, and inject the keys on the IPsec. So the establishment is used combining the classical with the IPsec keys, the QKD keys. So, well, here is the map with the partner involved and the environment. And here is the setup we created for demo purpose, basically with 3 G-Node-B or 3 antennas using post-quantum cryptography purely over the security gateways used on 5G, that is the IPsec, with the post-quantum in the left side, and in the right side we make the same, another 3 antennas with 3 users, but in this case we use the QDITO and the SSIPs, that is the controller for the IPsec, with the QKD keys. So before jumping to the demo, just to give you that one of the main conclusions we identify is, of course, having more complex technologies like including QKD impact on performance at level of resources that are needed on the systems, at CPU, memory. So this is an expected situation. That means that this solution should not be applied for everywhere. I mean, probably you have to select the places where this type of technology should be used. For example, thinking in terms of very high demanding or high security demanding clients like government, defense, or banks, where they are able to support this overhead and pay for that to using this complex technology. In terms of data plane and as expected, this is not impacted. In any case, we measure it, basically because we wanted to know if there is some impact, but in principle, based on symmetric encryption, should not be it. And where we have more impact is in the part of the setting up the connectivity and the rekeying process, where we have identified really a strong gap in the part of using the QKD. It's true that these high numbers is not so critical because, as you know, when we establish IPsec, is something you do depending on the scenarios, but on 5G network, usually you use every 24 hours, 18 hours, 12 hours. So in the general behavior of the system, is not relevant to have these times like 23 seconds to establish a tunnel. Nonetheless, this has been selected in the worst case. I mean, you have a QKD system that is triggered on, for example, after a call start, and you need to establish the quantum channel. All the physical properties have been included in the analysis in order to evaluate the worst scenario. The reality usually is that this number can be reduced to 1-2 seconds. We need to make more effort on that. So I don't know if we can have the video of the demo. So basically here, what we do is showing the graphical interface of the Cujata that is based on Grafana that show a lot of the metrics that can be measured during the experiment. For us, this is critical because it's one of the achievements of the project. I mean, to be able to have this evaluation framework to be used when we decide the final strategy for migrating the technology. Here we have the scenario based on this cloud environment with 3 G-Node-B UEs and the security gateways over a cluster on Kubernetes. What we're going to do is, having a couple of them already deployed, we will deploy only one for demo's purpose. Here is the classical one. As you can see in the right side, is using MLChem as the key exchange based on post-quantum cryptography. Here is also shown with the MLChem 512. And once we have this, we trigger the deployment of the tunnel and deployment of the user interface. We are not using any kind of fancy terminals and so on. What we want to do is measure the performance. So we use based on terminal information, we make the provision of the user on the 5G network and trigger the execution. So first, we use the interface from the open source 5G core. We make the provision of the user on the interface, and later on we trigger the connectivity in of the user to the network. And once we will have this user up and running, what we will do is basically make this performance test over the IPsec. So the first, we have the connectivity already in place. And now it's expected that we will show how the traffic will start to be injected on the network connection. So at the moment, there is no connection, no experiment. Here we use the Kujata framework, specifying all the parameters we want to use, the duration of the experiment, the size of the keys, the size of the traffic and the packets. And this interface, basically, when you click on the run button, will trigger and start to generate the traffic on the network as it is happening. Here you can see the traffic is encrypted over the IPsec. This is the ESP header you will see here. And this is being seen since the side of the antenna, let's say the G0 B. And in the right side here, you can see how it is detected on the server that is after the core, I mean on the data plane. And here we can start to collect a set of metrics that can be shown on the visual interface in the dashboard. So here start appear all the metrics that are being used. So this is for the part of the pure PQC IPsec based scenario. The idea is now to repeat the same experiment, but in this case, adding all the components we have mentioned related with the QDITO and the SESIP controller. So for that, basically, what we need to do is deploy all the components, the QDITO network, QKD network, emulation network, and also deploying, again, the user and the G0 B on all the components we have mentioned before. And again, we will have all the interfaces that will be used. Here, what we are going to show is the same. The G0 need. In this case, you have, as you can see, the proxies and the SSIP agent that are the one who is taking care of collecting the keys from the QKD and converting them in parameters that are injected in the IPsec using the QKD keys. Here is the control plane that is used to trigger the interaction. As you can see, here is requesting keys using the 014 512 size key, similar to the key we have used on MLChem, but in this case, a key coming from the QKD system. And once the QDITO environment responds, he's able to configure automatically all the IPsec with the QKD key obtained from the QKD system. And the tunnel is established and is running. This is the command that shows you how the tunnel is up and running. So once we have this, we can repeat again the process of provisioning the user and connecting the G0 B, connecting the user to the network, and generate again the traffic. So here is the session up with the user up and running. And again, we can go to the Kujata interface and repeat the process to generate all the traffic in a similar parameters that we have used on the side of the key, on the duration, and so on that have been shown before. But in this case, the keys is coming from the QKD system. So we play the run, and the traffic is still running again. And finally, we can see that we will also show that the interfaces is appearing with a new statistic on the Grafana interface. Well, these are the traffic, and here is the traffic and the statistic on low level, and here in the Cujata interface you can see all the parameters on the interface. So basically this is, I think we can stop it because this is the rest of the graphical with the performance and so on. So with this I finalize my presentation. Thank you.